Alright, so today I'm going to talk about Newman projections and how to draw them from a known molecule. So let's take, for example, butane. Butane, as we recall, is a 4-carbon alkane. Its formula is C4H10. I'm just going to draw it for you right here. Okay, so that's what we know as butane. And when we think about it, we imagine it in, the 4 carbons in a straight line. But obviously, if we were to look at an actual molecule, that is not how it would be arranged. So how would this molecule look if we were to actually look at the arrangement of the carbons on this molecule? Well, if we recall our geometric shapes from general chemistry, we can remember that we had linear, bent, tetrahedral, square planar, trigonal planar, and all of those. Well, these molecules are going to follow the same sort of arrangement. So in this case, one of the most common ones that we'll see in organic chemistry is the tetrahedral shape. And if we recall what it looks like, I'm going to draw one for you. It's something like this. Now, if you recall, these solid triangles represent coming out of the page, and the dashed line, like over here, represents something that's going into the page, and then these just straight lines are in the plane of the page. So that is what those symbols represent, in case you don't remember. And I'm going to draw the dotted lines in here just so we can kind of remember what this looks like. Envision it in 3D mode. So if you can see that, that is what we would call a tetrahedral. So a central atom with 4 branches coming off of it. And the angle between all of these is going to be 109.5. So 109.5 degrees, and that is the angle between all of those molecules there. So how would we apply this to the structure of butane? Well, it would look something like this. As we recall also, let's just say for reference later, that these are going to be carbons 1, 2, 3, and 4, like that. So over here, I'm going to draw carbons 2 and 3. Those are carbons 2 and 3. And then recall that also on all of these there are hydrogens. So that's where we get these tetrahedral shapes from. So let's say we have one going up like this. Now this is actually going to be a CH3, and that's actually carbon 4. And then we have a hydrogen and another hydrogen there. Another CH3 up here. This would be carbon 1. H. Okay, so that's actually what it would look like, that being carbon 1, 2, 3, and 4, and then the other points of the tetrahedral shape are going to be made up by hydrogens. So I don't know if you can kind of envision this here, but if you look at this and you turn it sideways, that's how we get the tetrahedral shape here, and I'm going to draw it. I'm going to draw in the dotted line so you can kind of see that. So if you can kind of see that there, and then the same thing would apply on this side. So that's how we get the tetrahedral shapes there. Alright, so what's interesting about molecules in general when they're single bonded is that they're free to rotate around each other. So if you have, let's say carbons 2 and 3 like this, they can rotate around that single bond in such a fashion. And, same with, carbons 1 and 2 and 3 and 4, they can rotate around each other. So let's say that we were looking at this molecule from this point of view. I'm going to draw an eyeball right here, you know, and then we're looking this way. And the point of seeing this is so that we can draw our Newman projection, because Newman projections are a way of drawing molecules such that the perspective is as if you are looking down the carbon and along the bond. So basically carbons 2 and 3 are on top of each other like this, and you're looking down this way. So if we were looking down this way, what would we actually see? And this is how I'm going to show you how to draw the Newman projection. So typically how we draw this is we're going to draw a circle, and you know, if we're looking down this bond angle like this, we can see that we have three points. So the bottom of the tetrahedral, there's 3 points. So 1, 2, 3. So then of course here in the center is where you would have the 1 carbon, and you know, the other carbon is directly, so this would be carbon 2 and carbon 3 would be directly behind it. So then also what we're going to draw is we're going to draw what we would see, you know, from these 3 points coming out. So I'm going to go ahead and draw those lines like this. So if you are looking at this tetrahedral this way or this way, that's how we are envisioning drawing this molecule here. So if we look down this way, we see that on top we have a CH3. And if we keep looking down this way, we also see that on top we have a CH3. So we're going to put that there. Coming out of the page, so if we're looking this way, it would be on our right, we have a hydrogen. So we're going to put that there. And on our left, we would have another hydrogen. So we're going to put that there. And the same thing occurs in this situation. On our right, we have a hydrogen. That would be this one. And on our left, we have another hydrogen. That would be that one. Because remember, the dashed line represents going into the page. So that's actually, you know, behind. So this one's coming out and that one's behind. So if we're looking at it, you know, it's like this, you know. This would be, you know, if we have it this way and then we turn it like this, this is a hydrogen coming out of the page here, and this is the hydrogen going into the page. So we have these 2 hydrogens there as well. So when we're looking at this, we see that these two, well, obviously, you know, a CH3 or a methyl group is going to be larger in size than just a hydrogen, because, you know, CH3, not only does it consist of 3 hydrogens, but it also consists of a carbon, which is very large compared to just a hydrogen. So these are considered bulky groups. So we can see in this arrangement that the bulky groups are on the same side of the molecule. So essentially, between them, there's 0 degrees. Now remember I said that molecules are free to rotate about their single bonds. So what we're going to be showing is basically this backside portion of the molecule rotating around this way. And so basically this way of drawing is what we call a Newman projection. So I'm going to show you what happens when we rotate that backside around the bond in between carbons 2 and 3. So this is called totally eclipsed. Totally eclipsed means that the 2 large groups are right on top of each other. Now I know, like, I left a little bit of space in between those 2 lines, but that's just to show you that, you know, that there's 2 lines there. But really what this is trying to show you is that there's 0 degrees of rotation in between these 2 bulky groups. So therefore this is called totally eclipsed, and that's 0 degrees. Now if we take this CH3 and rotate it about the bond in between carbons 2 and 3, I'm going to show you how it would look. The front stays the same. And then the back is rotating. So this one has moved here, This one has moved here, and this one has moved here. Now we see that there's 60 degrees in between those two methyl groups, and this is called gauche. It's having a gauche configuration. That's what we call this. And then, as you can see, if we rotate this one more time, another 60 degrees, I'll draw it over here. Again, I'm keeping the front the same. And then this one is rotating another 60 degrees here. Like that. That's 120 degrees of rotation. We can see that again, it is eclipsed just as it was here, but it's not totally eclipsed because the two large bulky groups are not on top of each other. So even though this configuration is still eclipsed, it is not totally eclipsed. I should have used red, sorry. And then finally, if we rotate it one more time, another 60 degrees. Again, keeping the front the same. And then we rotate it another 60 degrees. It's going to look like this. CH3, H, and H. We can see that now it has rotated 180 degrees from the start. And this is called anti. So when those two original groups are 180 degrees from each other, that's called anti. So basically, if it continues to go around, it basically goes back around this. It goes through this rotation basically again. It would just be the opposite, continuing the circle. So if the CH3 was then going to be over here at 240 degrees, it would again be eclipsed. And then if it was going to be over here at 300 degrees, then it would be gauche. And then if it was back up here, it would be totally eclipsed. So basically it goes totally eclipsed, gauche, eclipsed, anti, eclipsed, gauche, totally eclipsed, and it keeps going through that rotation again. So, and these pictures here with the circles and then the three sticks coming out of it, that's what we call a Newman projection. And these are the different conformations that we can have. And for this example, I just used butane. So this is actually what butane would look like, since it is not actually ever going to be in a straight line as we draw it. So yeah, that's a Newman projection. Thank you.